For nearly all of human history, they were omens. Uninvited guests in the placid clockwork of the night sky. Their sudden, silent appearance was a tear in the fabric of the cosmos, a message written in ethereal light. Kings and conquerors saw in their ghostly tales the spectre of their own doom, or the divine sanction for their ambitions. To civilizations across the globe, these celestial phantoms were harbingers of flood and famine, of revolution and the fall of empires. They were not objects to be understood, but portents to be feared, celestial messengers, delivering a verdict we could only guess at. We painted them on cave walls, chronicled their visits in sacred texts, and wove their eerie beauty into the very tapestry of our myths. They were the universe speaking to us in a language of pure, terrifying spectacle, a language we spent millennia trying to decipher. The long, slow dawn of reason began to strip them of their supernatural dread, but not their capacity for wonder. We learned they were not tears in the sky, but travelers on epic journeys governed by the same invisible laws that hold our own world in its orbit. We discovered they were citizens of our own solar system, ancient icebergs, laden with the dust of creation preserved in the deep freeze of interstellar space for billions of years. They became frozen time capsules carrying within their fragile nuclei the primordial chemistry from which our planets, our oceans, and perhaps even we ourselves were born. They were no longer omens, but opportunities, celestial laboratories delivered to our doorstep, offering us a glimpse into the universe's infancy. With every close pass of a Halley, a Hale-Bopp, or a Hyakutake, we sharpened our tools and our understanding, moving from fearful observers to inquisitive explorers. We no longer waited for their verdicts. We sent our own robotic emissaries like the Rosetta spacecraft to rendezvous with these icy ghosts, to touch them, to taste their vaporous breath, and to listen to the secrets they had held in silence since before the Earth had cooled. In this new age of discovery, we built sentinels, not towers of stone, but domes of polished steel and silicon, our sleepless digital eyes scanning the heavens without pause. One such network, a shield against cosmic threats, is the Asteroid Terrestrial Impact Last Alert System, ATLAS. Its mission is to find the rocks that could do us harm, to chart the orbits of near-Earth objects with relentless precision. It is a profoundly practical endeavor, a planetary defense system born of cold, hard calculation. But in the final days of 2019, this sentinel designed to spot danger close to home found something else entirely. It flagged a faint, unassuming smudge of light moving out in the cold darkness beyond the orbit of Mars. Catalogued as A 2019 Y4, it was just one of countless such discoveries made every year. Yet, as astronomers refined its path, a wave of palpable excitement began to build, rippling through the global community of skywatchers. This was no ordinary cosmic vagabond. The trajectory was immense, a vast, sweeping parabola that hinted at an origin of unimaginable distance and antiquity. This was not a short-period comet trapped in a recurring loop around the Sun, its life bleeding away with each fiery pass. This was a long-period wanderer, a pristine relic likely hurled inwards from the Oort Cloud, that theoretical spherical shell of trillions of frozen bodies encasing our solar system like a ghostly egg. This traveller was a direct link to the birth of everything we know, its journey towards our Sun lasting millions of years, a solitary pilgrimage from the absolute fringe of the Sun's gravitational kingdom. For astronomers, this was the equivalent of discovering a perfectly preserved manuscript from a lost civilization. A comet like this, on its very first plunge into the inner solar system, promised to be uniquely volatile, its surface layers rich with exotic ices that had never before felt the warmth of a star. It had the potential to outgas stupendously, to bloom into a magnificent spectacle visible to the naked eye. A true great comet of the kind that graces our skies only once a generation. But there was another, even more tantalizing possibility whispering through the data. The orbit was so extreme, so steeply inclined, that it flirted with the very edge of possibility. It looked almost unbound. Its path was so close to the gravitational escape velocity of the Sun that it begged a profound question. Was it truly one of ours? Or could it be something far rarer, a visitor from another star system entirely? We had only ever confirmed two such interstellar objects before the enigmatic, cigar-shaped rock known as Oumuamua and the more conventional but still extraordinary comet 2I, Borisov. The prospect that this new discovery might be the third interstellar interloper, an alien comet from a distant, unknown sun, ignited a firestorm of interest. Some began to refer to it, hopefully speculatively, as 3I Atlas, the third of its kind. The world's great observatories swiveled to track its approach, every telescope that could be spared locking onto its faint but growing form. Professional and amateur astronomers alike held their collective breath, anticipating a celestial performance for the ages. Here was a messenger not from the gods but perhaps from another star, and it was headed our way, and then Atlas began to behave strangely. At first, the anomaly was a welcome one. Through January and February of 2020, it began to brighten at a ferocious, almost unprecedented rate. It was far exceeding even the most optimistic predictions, its luminosity increasing so rapidly that it seemed destined to become one of the brightest objects in the night sky. The activity was explosive. We imagined its virgin surface, warmed by the sun for the first time in 4.5 billion years, beginning to crack and fizz. We pictured jets of ancient supervolatile ices, carbon monoxide, nitrogen, perhaps substances we had yet to properly understand, erupting into space, releasing a torrent of dust that caught the sunlight and created a rapidly expanding, brilliant shroud. The show was starting early, and it was spectacular. The comet was putting on a performance that suggested a colossal active nucleus, a true giant awakening from an eon of slumber. It was as if this cosmic pilgrim, after its near-eternal journey through the cold, was roaring its arrival, announcing its presence with a flare of celestial energy that promised an unforgettable climax as it rounded the Sunday. But the roar soon faltered, turning into a perplexing whisper. Just as the excitement reached its peak, the comet's brilliant ascent suddenly inexplicably stopped. In mid-March, the steep curve of its brightening flattened out. It stalled. For a comet, this is a deeply unnatural act. Its journey towards the sun is a one-way street into an inferno. As it gets closer, the solar radiation bombarding it intensifies exponentially. The heating increases, the sublimation of its ices should accelerate, and the comet should, by all known laws of physics, get brighter and brighter. For it to simply stop to hit a plateau while still hurtling towards the solar system's central furnace was baffling. It was like watching a rocket halfway through its launch suddenly cease to accelerate its engines, sputtering against the pull of gravity. The community watched, puzzled, as the great comet's momentum vanished. What could possibly cause such a thing? Had it already exhausted its most volatile surface materials? Was it coated in a thick, insulating crust of dust that was choking off the vents? The mystery deepened. Analysis of its trajectory revealed another anomaly, one that seemed to defy logic. The comet wasn't just stalling in its brightness, it appeared to be decelerating its activity. This isn't a deceleration in the traditional sense, like a car applying its brakes. Comets don't have brakes. Their paths are dictated almost entirely by the sun's immense gravity. However, their orbits are subtly altered by what are known as non-gravitational forces. These are the very jets of gas and dust that make a comet glow. As ice vaporizes and shoots out from the nucleus, it acts like a tiny, unpredictable network of rocket thrusters, gently pushing the comet's nucleus this way and that. For an active comet like Atlas, these forces are a signature of its vitality. But with Atlas, these forces seem to be fading, weakening far more quickly than they should have been. The celestial engine was winding down. It was as if the comet itself was giving up its internal heart-light dimming even as it plunged into the brightest part of its journey. This slowdown was the most ominous sign of all, a troubling tremor from the core of the object itself. It suggested a profound systemic failure was underway. The grand spectacle was being cancelled before our very eyes, and we had no idea why. The final act of this celestial tragedy was captured in heartbreaking detail by the unblinking eye of the Hubble Space Telescope. In late April, astronomers pointed the legendary observatory at the fading comet, hoping to understand what was happening to its core, its nucleus. What they saw was not a single solid object, but a funeral procession. Where a single vibrant nucleus should have been, there was instead a ghostly chain of shattered fragments, small dim pieces of ice and rock drifting apart in the darkness. The great comet was dead. It had not been killed by a collision, nor had it been ripped apart by the gravity of a giant planet. It had, for all intents and purposes, simply disintegrated. It had fallen apart under the gentle, persistent pressure of the sunlight, its internal structure too weak to withstand the transition from the cosmic deep freeze to the warmth of the inner solar system. The promise of a generational spectacle had dissolved into a cloud of cosmic debris, a faint, sad smudge where a brilliant beacon was meant to be. The celestial messenger had arrived, but its message was fragmented, its script torn to pieces before it could be read. It had self-destructed, performing a baffling act of celestial suicide. We were left with a profound and haunting puzzle. The story of Comet Atlas is not one of triumph but of failure. Yet, in science, failure is often a far more potent teacher than success. This wanderer, which had journeyed for millions of years from the darkest frontiers of the solar system, perhaps even from the void between the stars, did not give us the brilliant show we had hoped for. Instead, it gave us something far more valuable, a deep and enduring mystery. It forced us to confront how little we truly know about the life and death of these icy pilgrims. What made Atlas so fragile? Was it a clue to its origin, a sign that objects from the outermost Oort Cloud are fundamentally different, more delicate than those we have studied before? Was its composition unique, containing ices that created a flash of brilliance before destroying the very body that housed them? Or was its strange sputtering demise its deceleration? Evidence of a process of cometary decay we have never before witnessed. With such clarity, the questions left behind in its dusty wake are immense. We set out to observe a simple spectacle of light and ice, but found ourselves conducting a celestial autopsy, searching for clues in the ghost of a comet that defied our every expectation. To understand what happened to Atlas is to seek a deeper understanding of the very architecture of our solar system and the nature of the countless voyagers that still drift silently in the unending darkness. What if the most profound story of our own origins wasn't buried deep within the Earth, but was instead falling towards us from the blackest voids of space? Imagine a messenger silent for over 4.5 billion years, a perfect time capsule carrying the chemical recipe that built our world, our sun, and even ourselves. This isn't science fiction. This is the solemn promise of every comet, a ghostly wanderer sent from the farthest, coldest frontiers of our solar system. To understand the story of the object that would captivate and utterly baffle us, we must first journey to these forgotten realms, the great nurseries of cosmic ice. We must travel to a place so far from the sun's warmth that our star is just the brightest point of light in a sea of infinite night. Out there, far beyond the orbit of the most distant planet, lies a kingdom of ghosts. It isn't a belt or a ring, but an immense spherical shell of cosmic debris, a hollow globe of primordial material encasing the entire solar system. We call it the Oort Cloud. It is a concept more than a destination, a gravitational whisper stretching almost a light year into the abyss, marking the very edge of the sun's dominion. Here, trillions of icy bodies, remnants from the planetary construction yard, drift in a state of suspended animation. They move with an impossible slowness, their orbits measured not in years but in millions of years, held in a delicate gravitational balance. They are the pristine archives of creation, composed of the same water ice, frozen gases, and carbon-rich dust that coalesced to form the planets. They have slumbered in a darkness and cold so profound, just a few degrees above absolute zero, that their chemistry has remained utterly unchanged since the dawn of our solar system. They are the baby pictures of our cosmic family, preserved in the deepest freeze imaginable. For eons they drift in this silent, lonely ballet. But the galaxy is not a quiet place. The gravity of a passing star, a subtle nudge from the collective pull of the Milky Way itself, or a gentle jostle from a wandering molecular cloud, can disturb this fragile peace. One of these frozen relics, perhaps no larger than a city block or a small mountain, can be dislodged from its ancient stable path. Its orbital energy shifts ever so slightly. It begins a long, slow fall, a journey that will take millennia to complete. Pulled by the sun's relentless gravity, it accelerates, crossing the immense void, a solitary traveller on a voyage towards a fire it has never known. This is the genesis of the long-period comets, the spectacular visitors that grace our skies. Perhaps once in a human lifetime, their magnificent tails, a temporary brushstroke against the canvas of the stars. They arrive as strangers from the deep, reminding us of the vast unseen architecture that surrounds our tiny sunlit island of life. They are echoes from the outer darkness, carrying secrets of our own conception. Closer in, though still deep in the planetary twilight zone beyond Neptune, lies another reservoir of these celestial fossils, the Kuiper Belt. Unlike the spectral, all-encompassing Oort Cloud, this is a flatter, more crowded disk of icy bodies, a cosmic junkyard teeming with dwarf planets like Pluto and countless smaller worlds. This is the home of the short-period comets, those with orbits of less than 200 years like the famous Halley's Comet. They are the more frequent, more predictable visitors, yet even they are messengers from an antique past, sculpted by the gravitational tug-of-war between the giant outer planets. Whether they are flung inwards from the Kuiper Belt or fall from the distant Oort Cloud, every comet begins the same transformative journey. As it crosses the frost line, the critical distance where the sun's radiation becomes strong enough to sublimate its ices, the miracle begins. The frozen gases, carbon dioxide, methane, ammonia, erupt from its surface, bursting forth into space and dragging with them vast quantities of dust. This cloud of gas and dust, the coma expands to become larger than a planet, a temporary atmosphere surrounding the tiny solid nucleus. The solar wind, a constant stream of charged particles flowing from the sun, then pushes this material away, sculpting it into two distinct, glorious tails. One, the ion tail, is made of glowing gas, pushed straight back from the sun like a celestial windsock, often shining with an eerie blue light. The other, the dust tail, is a broader, more gracefully curved plume of fine particles, reflecting the golden light of the Sunday. This is the spectacle. You see the transformation of a dark, inert piece of ice and rock into one of the most sublime sights in all of nature. It is a process of self-destruction, a beautiful, fleeting death scene played out over months as the comet sheds its ancient layers into the vacuum of space. Each visit strips it of its volatile materials until eventually, after countless passages, it becomes a dark, inert husk, its story finally told. Every bright comet is therefore a new story, a fresh chapter from the solar system's genesis delivered to our doorstep for a brief, glorious moment. And in the final days of 2019, our robotic sentinels detected a new messenger beginning its fall, a messenger that promised to be unlike any we had ever seen. The discovery wasn't made through the eyepiece of a lone astronomer shivering in a cold observatory dome. It came as a quiet string of data, a few anomalous pixels of light flagged by an algorithm. The source was the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a pair of robotic telescopes in Hawaii and Chile. Their mission is not one of poetic discovery but of planetary defense. They scan the entire observable sky every few nights, their unblinking eyes searching for any faint point of light, moving against the background stars, hunting for asteroids that might pose a threat to Earth. On December 28, 2019, the system did its job. It registered a faint new object catalogued initially as A 2019Y4. The A designated it as an asteroid, the default classification for any new rocky-looking body. But astronomers who followed up on the automated alert quickly saw something the machines had not. The tiny dot of light was not sharp and stellar. It was fuzzy, indistinct, surrounded by a faint telltale haze. This was no asteroid. This was a comet, and it was behaving very, very strangely. At the time of its discovery, Comet Atlas was an incredibly distant and faint object, nearly 3 times farther from the Sun than the Earth is. An object this far out in the frigid expanse between the orbits of Mars and Jupiter should have been little more than a frozen, inactive rock, yet it already sported a visible coma. Even more remarkably, it was brightening at a blistering, almost unprecedented rate. Cometary brightness is a notoriously difficult thing to predict, but Atlas was shattering all expectations. As weeks turned into months, its light curve, the graph of its increasing brightness, was steeper than almost any comet on record. It was outshining predictions, not by a little, but by factors of hundreds and then thousands. Extrapolating this dramatic trend forward, astronomers began to whisper. Then they began to shout. The calculations suggested that by the time it reached its closest approach to the Sun in May of 2020, Comet Atlas could become brilliant. truly magnificently brilliant. It might become a great comet, a rare celestial event, an object so bright it would be easily visible to the naked eye, even from light-polluted cities. Some of the more audacious predictions suggested it could rival the planet Venus in the twilight sky, its tail stretching like a ghostly feather across a huge swath of the northern heavens. The world was hungry for a spectacle, and Atlas seemed poised to deliver the celestial performance of a generation. The media caught on, and anticipation began to build across the globe. But among the specialists who track these cosmic travelers, the comet's extreme behavior was raising profound questions. Why was it so active, so far from the Sun? One possibility was that it was enormous, a truly gigantic nucleus of ice, hundreds of kilometers across something far larger than a typical comet. A larger surface area would mean more ice exposed to the weak sunlight at that distance, generating a larger coma. If this were true, the spectacle it would unleash as it neared the Sun would be beyond anything seen in modern history. Another more subtle theory was that we were seeing it during a rare explosive outburst, a temporary flare-up that would soon fizzle out. Or perhaps its surface was covered in exceptionally volatile superices like frozen nitrogen or carbon monoxide, which turned to gas at much lower temperatures than water ice. This would explain the early activity, but might mean the show would be over before it truly began, as these surface layers were blasted away. The comet was a mystery box, a puzzle falling towards us at over 100,000 miles per hour, and its perplexing brightness was only the first piece of the enigma. The second piece would arrive just a few weeks later, a discovery so shocking it threatened to rewrite the comet's entire identity. As observatories around the world turned their attention to the rapidly brightening object, they began to collect more and more precise measurements of its position. With each new data point, astronomers could refine their calculation of its trajectory, its exact path through the solar system. The orbit of an object tells you its history. An elliptical closed orbit means it's a member of our solar system gravitationally bound to the Sun, destined to return again and again. But there is another kind of path, a hyperbolic orbit. This is the signature of an outsider. An object on a hyperbolic trajectory is moving too fast to be captured by the Sun's gravity. It is on a one-way trip, a cosmic slingshot that will whip it around our star and fling it back out into the void, never to return. A hyperbolic orbit means the object did not originate here. It came from interstellar space. It is a visitor from another star system. In early 2020, the initial orbital solutions for Comet Atlas, based on the early limited data, hinted at exactly this. The numbers suggested its path was not a closed ellipse, but a slight, yet distinct hyperbola. The news sent a shockwave through the astronomical community. We had only ever confirmed 2 interstellar visitors before. First came one, Oumuamua, in 2017, a bizarre cigar-shaped object that tumbled end over end and showed no cometary activity, baffling scientists. Then came 2I, Borisov, in 2019, which looked and behaved much more like a conventional comet, giving us our first real sample of the building blocks from another star's planetary system. The possibility that a third interstellar object had been found so soon after the first 2 was electrifying. The official designation reflected this tantalizing prospect. For a brief, thrilling period, the comet was christened 3I, Atlas. The I stood for interstellar. The number 3 proclaimed it as the third confirmed traveller from the gulf between the stars. The implications were staggering. If it was truly from another star, its spectacular brightness was even more significant. We weren't just about to witness a great comet, we were potentially about to get our best look ever at the raw material from an alien solar system. What secrets did it hold? Was the composition of its ices the same as our own comets, suggesting the chemistry of life is universal, or would its spectrum reveal exotic isotopes and molecular ratios, a completely different chemical fingerprint? From a star system born in a different corner of the galaxy, the scientific potential was immense. An interstellar comet, especially one as large and active as 3I, Atlas appeared to be, was a scientific goldmine. It was a free sample of another world delivered right to our neighborhood. Instruments that could parse the chemical makeup of its coma telescopes, that could study the physical properties of its nucleus, All were being prepared for what was billed as a once-in-a-career opportunity. This object was no longer just a curiosity, it was a cosmic ambassador. The story was perfect. A mysterious messenger arriving from the stars, putting on a dazzling light show for all of humanity, while offering scientists a glimpse into the nature of worlds beyond our own. The excitement was palpable, a potent mix of public awe and intense scientific focus. The stage was set for a celestial event that would be remembered for centuries. As more data poured in, however, the story began to shift. With a longer observation arc, astronomers were able to trace the comet's path backward in time with much greater precision. The new, more robust calculations painted a different picture. The orbit wasn't hyperbolic after all. It was an extremely long-period ellipse, so stretched out and vast that it was almost indistinguishable from a one-way path. The comet, it turned out, was a native of our own solar system. It was a child of the Oort Cloud, not a stranger from another star. The 3I designation was quietly dropped, and the comet was reclassified back to C, 2019 Y4 Atlas, with the C denoting a long-period comet. For some, this was a disappointment. The dream of studying a pristine interstellar visitor had vanished. But for others, the mystery only deepened. If it wasn't an interstellar object, then it was one of our own, and its behavior was still absolutely extraordinary. In fact, its origin story became even more compelling. The new orbit suggested it had a period of roughly 4,000 to 6,000 years. This meant its last and possibly only visit to the inner solar system was at the dawn of human civilization long before recorded history. It was, for all intents and purposes, a virgin comet making its first fiery passage around the Sunday. This could explain its manic activity. A fresh comet from the Oort Cloud would have its entire surface covered in those highly volatile ices, which would sublimate with incredible vigor upon feeling the sun's warmth for the very first time. The interstellar hype faded, but the promise of a spectacular show remained now rooted in a different but equally fascinating narrative. This was a true primordial relic, an untouched piece of creation, and it was still on track to become one of the brightest comets in decades. The scientific mission was still critical. Studying a first-time visitor like this provides the purest possible sample of the original solar nebula. The anticipation, both public and scientific, recalibrated and continued to build towards its peak in the spring of 2020. Everyone was looking up, waiting for this ancient messenger to round the sun and blaze into our evening sky. We were watching a 4.5 billion-year-old story reach its climax. But this comet had a secret. Its dazzling brightness wasn't a sign of strength. It was a cry for help, and its epic journey from the dawn of time was about to come to a sudden, dramatic, and completely unexpected end. And so, with its trajectory plotted and its alien origin confirmed, the astronomical world settled in for the show of a lifetime. The great observatories and the legions of devoted amateurs in their backyards all turned their gaze toward this singular point of light, a traveler carrying the secrets of another star. We were watching the overture of a spectacular cosmic performance. Every new measurement, every updated light curve seemed to reinforce the initial breathtaking prediction. As Atlas fell toward the sun, its surface, a cocktail of primordial ices frozen for billions of years, was beginning to feel the warmth. The physics was supposed to be simple, elegant, and predictable. Heat from our star, even at this vast distance, should act as a celestial blowtorch, turning solid ice directly into gas in a process called sublimation. This expanding cloud of gas and dust, the coma would catch the sunlight, growing larger and more brilliant with each passing day. The light curve, the graph of its brightness over time, was meant to be a smooth, inexorable ramp toward glory. It was a script written by the fundamental laws of thermodynamics and gravity, a script we had seen countless comets from our own Oort Cloud follow with near-perfect fidelity. For a few precious weeks, Atlas obliged. It was a model student of cometary science, its brightness climbing the charts exactly as forecasted. The celestial crescendo was building. We were on the cusp of witnessing a truly naked-eye interstellar object, a ghostly green lantern hanging in our night sky. But then, something began to falter. It wasn't a sudden catastrophic event, not a dramatic change that would seize headlines overnight. Instead, it was a subtle, almost imperceptible deviation. a ghost in the machine. The first signs emerged not as a clear signal but as a nagging doubt in the minds of those watching most closely. The data points meticulously plotted on the light curve began to drift. They started to fall just slightly below the predicted line of ascent. At first it was dismissed. Perhaps it was a calibration error in a single telescope. Maybe a patch of cosmic dust was momentarily obscuring our view. The universe is a messy place and perfect data is a myth. But the trend persisted. More observatories reported the same quiet anomaly. The data points were no longer just drifting. They were forming a new, shallower curve. The inexorable ramp was beginning to level out. The engine of sublimation, which should have been roaring to life, seemed to be sputtering. Astronomers began to use a curious counterintuitive term to describe what they were seeing. They called it deceleration. Of course, the object itself wasn't slowing down its physical journey through space. Gravity had it in an unyielding grip, pulling it faster and faster toward its solar rendezvous. The deceleration was in its activity. The rate at which it was brightening was slowing dramatically. Imagine a firework rocket ascending into the night sky, its brilliant flame pushing it higher and higher. Now imagine that flame, instead of burning brighter as it climbs, begins to flicker, to shrink, to lose its vigorous power. The rocket continues its upward arc for a time, but its driving force is mysteriously failing. This was Atlas. It was a performance that had lost its momentum, an actor that had forgotten its lines in the middle of the second act. The celestial crescendo had hit a discordant note, a prolonged, unsettling silence that echoed through the digital forums and academic departments of the astronomical world. This wasn't just a minor puzzle, it was a fundamental challenge to our understanding. The standard model of a comet is built on a foundation of straightforward assumptions. A comet is a dirty snowball. The closer it gets to the fire, the more of that snowball melts and turns to steam, making a bigger, brighter cloud. This relationship between distance and brightness is one of the most well-established pillars of cometary science. You could practically set your clock by it. Yet here was an object from another solar system, a priceless sample of an alien environment refusing to play by the rules. It was as if we had invited a guest to dinner who, upon being served a familiar meal, began to eat it with an instrument we had never seen before. The very simplicity of the situation was what made it so baffling. All the conditions for a spectacular outburst were improving. The sun's energy bathing its surface was increasing with every passing second. The temperature on its nucleus should have been climbing, steadily triggering ever more violent jets of gas and dust. Instead, the opposite was happening. The comet's light was stagnating, its majestic coma appearing to thin, to lose its crisp, defined edge. It was a profound contradiction, a paradox playing out across millions of miles of empty space. The robust predictive models that had worked for Halley, for Hale-Bopp, for Neowise were failing spectacularly for Atlas. The script was being thrown out, and we were left watching an improvisation whose rules we could not comprehend. The question rippled through the community: what could possibly put the brakes on a process driven by the raw, unfiltered power of a star? What force, what unknown property of this alien artifact could defy such basic physics? The first and most straightforward hypothesis was also the most disappointing. Perhaps Atlas was simply running out of fuel. In this scenario, the object was never a great monolithic snowball to begin with. Instead, it might have been a mostly rocky or dusty body, coated with a thin, superficial veneer of hypervolatile ices, like frozen carbon monoxide or nitrogen. These substances sublimate at incredibly low temperatures, far out in the frozen depths of the solar system. The initial surge in brightness that had so captivated us wasn't the beginning of a sustained performance. It was the entire time's performance. We had witnessed the flash boiling of its outermost, most fragile layer. Now that layer was gone, burned off into space. What was left behind was a darker, more inert core, a rocky husk that simply couldn't produce the vast clouds of gas and dust needed to continue brightening. It was an elegant, if somewhat anticlimactic explanation. It suggested that Atlas was an interstellar dud, a cosmic firecracker that fizzled after its initial ignition. This theory fit the initial data of the stalled brightening quite well. It explained the early promise and the subsequent failure. But it also carried with it a profound implication. If this were true, it would mean that the surfaces of objects from other star systems could be fundamentally different from those in our own. Perhaps in the protoplanetary disk where Atlas was born, this kind of superficial icy coating was the norm. It would be a crucial clue about the chemistry of other stellar nurseries. Yet some astronomers remained skeptical. The deceleration seemed too controlled. A simple burn-off might be expected to be patchy and uneven, causing fluctuations and flutters in the light curve. What they were observing was a smoother, more deliberate leveling off, as if a dimmer switch were being slowly turned down on the entire object. The dud theory felt too simple for such a strangely graceful failure. This skepticism gave rise to a second, more complex and intriguing idea, the mantle hypothesis. This theory proposed that Atlas was not running out of fuel, but that its fuel was being trapped. As the sun's heat began to sublimate the ices on the nucleus, it didn't just release gas. It also liberated vast quantities of dust, grit, and rock that had been trapped within that ice for eons. In the initial phase, this mixture of gas and dust erupted violently into space, forming the beautiful expanding coma. But according to the mantle hypothesis, not all of that dust escaped. Some of the larger, heavier particles lacking the velocity to escape the nucleus's feeble gravity would have been thrown up only to fall back down onto the surface. Over time, this process would create a suffocating blanket of its own debris. An insulating crust or mantle of dark, non-volatile dust would begin to cover the pristine ice below. You can imagine it like a layer of ash smothering the glowing embers of a fire. The fuel is still there, the heat is still present, but the reaction is being choked off. This dark, dusty layer would be incredibly effective at preventing the sun's energy from reaching the volatile ices buried beneath. It would absorb sunlight, heat up, and radiate that heat back into space, rather than conducting it down into the heart of the comet. The process of sublimation would grind to a halt, not because the ice was gone, but because it had been hermetically sealed beneath a protective shield of its own making. This self-quenching mechanism was a known phenomenon observed in some comets from our own solar system as they age and become dormant. Perhaps we were seeing this process happen on an accelerated timescale. Atlas, in its first pass through a truly warm inner solar system, was aging catastrophically, building its own cocoon and shutting itself down right before our eyes. Yet a third school of thought emerged, one that painted Atlas not as a simple object, but as a complex, heterogeneous world in miniature. This hypothesis centered on its rotation. We knew Atlas was spinning just as every celestial body does. But what if it wasn't a uniform, homogeneous snowball? What if its composition varied wildly across its surface? Perhaps one side of its nucleus was incredibly rich in volatile ices, a veritable fountain of cryogeysers waiting to erupt. Another side, however, could be composed almost entirely of dark, barren rock, a geological desert. As it traveled through space, rotating slowly, different terrains would be presented to the Sunday. The initial spectacular brightening could be explained if by pure chance we were observing its highly active icy hemisphere during its initial approach. For weeks this wet side faced the sun, driving the ferocious outgassing that put it on track for greatness. But as the object continued its journey and its rotational orientation shifted, this active region would have slowly turned away from the sun's direct glare. The rocky, inert, dry side would have rotated into view. The effect would be immediate and dramatic. The primary engine of cometary activity would be shut off not by a lack of fuel or an insulating mantle, but simply by the turning of the object itself. The light curve wouldn't just decelerate, it would plateau, reflecting the vastly reduced output from the barren terrain now facing the solar furnace. This idea was tantalizing because it transformed Atlas from a simple projectile into a complex body with its own geography, its own distinct hemispheres of activity and dormancy. It implied a formation history that was messy and complicated, a story of accretion and collision that resulted in a lopsided, non-uniform world. Trying to distinguish between these hypotheses became the central drama. Was it a hollow firework, a self-smothering ember, or a two-faced wanderer? Each theory carried vastly different implications for what this object was and for the nature of the planetary system it came from. Without a way to see the nucleus directly, an impossible feat from such a distance, we were left to argue over the shadows on the cave wall, trying to deduce the nature of a beast from its faint and fading ghost. The scientific community, once united in its anticipation, was now fragmented into competing camps, each championing their preferred explanation for the baffling behavior of our interstellar guest. The vigil had transformed into a frantic, high-stakes detective story, and the clues were getting stranger with every passing night. Atlas was no longer following any script, and the next act in its unpredictable performance was about to begin, promising a new layer of mystery that would make this initial slowdown seem like a gentle prelude to a far more violent and inexplicable transformation. The silence from Atlas was becoming deafening. Out there in the cold vacuum between Mars and Jupiter, the beacon that had promised a celestial spectacle for our world was now a fading whisper. Its light curve, once a triumphant climb towards glory, had become a troubling, precipitous fall. For weeks we had watched this downward slope, a graphical representation of a dying hope. The deceleration, that initial profound mystery, that strange, impossible act of braking against the sun's pull, was now accompanied by this pervasive dimming. It felt less like an engine throttling down and more like a fire being starved of fuel. Across the globe, in the quiet hum of observatory control rooms, the mood had shifted from excited anticipation to a kind of tense, collective bewilderment. Every new data point confirmed the last. Fainter, slower, fainter, slower. The comet was actively refusing its appointment with destiny, choosing instead to recede into the background noise of the cosmos. Initial theories, those beautiful wild speculations about outgassing jets acting as asymmetric thrusters, began to fray at the edges. The numbers just weren't adding up. The amount of gas and dust required to produce such a significant change in velocity to act as a cosmic retro-rocket should have been turning Atlas into a brilliant, magnificent fan of light. Instead, we were witnessing the exact opposite. It was a paradox wrapped in an enigma, a celestial object that was simultaneously pushing back against the sun while visibly shrinking from its gaze. This wasn't just a simple puzzle anymore. It was an affront to our models, a violation of the elegant, predictable ballet of orbital mechanics. Comets, for all their chaotic beauty, are creatures of habit. They follow Kepler's laws with slavish devotion, their paths carved by the immutable force of gravity. The subtle nudges from vaporizing ices are understood, predictable deviations that we can account for. But this was something else entirely. This was a ghost in the machine. The professional disappointment was palpable. The great comet of 2020, the one we had promised you, the one set to blaze across our spring skies, was failing. But for the scientists, disappointment was being rapidly replaced by a far more potent emotion, an insatiable, nagging curiosity. The failure of a comet can be more instructive than its success. A perfect, predictable journey teaches us what we already know. A body that breaks the rules, however, forces us to ask new questions. It was time to stop watching the light curve on a screen and to get a closer look. It was time to stare into the heart of the anomaly. A request was made, an urgent appeal sent up the chain of command of observational astronomy. We needed more than the wide-field surveys that had discovered Atlas. We needed more than the dedicated but limited view of amateur equipment. We needed power. We needed resolution. We needed to turn one of humanity's greatest eyes toward this fading spectre. We needed the Hubble Space Telescope. Floating high above the distorting haze of Earth's atmosphere, Hubble is our sentinel in the dark, a witness to cosmic events with a clarity that ground-based observatories can only dream of. To commandeer its time is no small feat. Its schedule is meticulously planned, months, even years in advance, a precious resource allocated to the most profound questions in astrophysics. But the case for Atlas was compelling. Here was an interstellar visitor, or perhaps a long-lost native behaving in a way we had never seen before. The request was granted. For a few precious orbits, the legendary telescope would suspend its search for distant galaxies and nascent solar systems. It would turn its gaze inward, focusing on a single puzzling point of light in our own cosmic backyard. The instructions were coded, translated into binary, and beamed across the void to the orbiting observatory. Slowly, with the silent, deliberate grace of a gravitational gyroscope, the immense telescope began to turn. Its great mirror, a marvel of engineering, swiveled away from the deepest reaches of space-time and locked onto the coordinates of the celestial phantom. The anticipation during those hours was immense. We had been watching a shadow on a cave wall interpreting the vague form of a dying object from millions of miles away. Now we were about to see its face. The data began to stream down, relayed from orbit to receiving stations on Earth, then piped through secure networks to the Space Telescope Science Institute. It arrived not as a beautiful, fully formed picture, but as a river of raw numbers, a flood of photons counted and catalogued by Hubble's sensitive instruments. Algorithms went to work cleaning the data, removing cosmic ray hits, stitching together exposures, translating the cold, hard numbers into a visual representation of a tiny patch of sky. On screens, the image began to resolve. First, the familiar background of distant, indifferent stars, each a perfect pinpoint of light. Then, at the center, where Atlas was supposed to be, the fuzzy, indistinct glow of its coma began to take shape. It was there just as expected. Faint, diffuse, a pale green mist against the black. But as the processing continued and the image sharpened, a collective intake of breath could be felt across the virtual rooms where scientists were watching. Something was profoundly, irrevocably wrong. Where there should have been one bright star-like point of light, a single solid nucleus hiding within the gas, there was nothing. Or rather, not one thing. The heart of Comet Atlas was gone. In its place was a scene of utter silent devastation. The image was shocking, unambiguous, and brutally clear. Hubble revealed not a comet, but the ghost of a comet. What we saw was not a single cohesive body. Instead, there was a loose, elongated chain of smaller, fainter objects, a ghostly procession of icy debris. It looked like a string of pearls cast carelessly across black velvet, each bead a fragment of a once mighty whole. The brightest piece, presumably the largest remnant of the original nucleus, led the grim parade. Behind it, trailing in a near-perfect line, were two, then three, then more distinct points of light, each with its own faint, misty tail. They were all moving together, a phantom limb of the object that had been a family of ghosts travelling along the path of their parent. The mystery was over. The great comet wasn't parking. It wasn't dimming because of some strange surface chemistry. It wasn't decelerating because of some mysterious unseen rocket engine. Comet Atlas was decelerating because it was dying. It was falling apart. The revelation was like a lightning strike, instantly illuminating everything we had been struggling to understand. The pieces of the puzzle, which had seemed so disconnected, so paradoxical, now snapped into place with breathtaking clarity. The deceleration was no longer a mystery. As the nucleus fractured, it unleashed huge chaotic bursts of gas. These weren't the gentle, predictable jets of a healthy comet. This was the explosive outgassing from a body breaking under stress. Fresh ice buried for billions of years was suddenly exposed to the sun, flash vaporizing with violent force. This chaotic release of energy pushing in multiple directions at once, as the fragments tumbled and spun, was acting as an erratic brake. It was the celestial equivalent of a ship deploying a sea anchor, creating immense drag against the relentless pull of the solar wind and gravity. The comet was slowing down because the very act of its own destruction was robbing it of its forward momentum. And the dimming, that too, now made perfect tragic sense. A comet's brightness comes from its coma, the vast cloud of gas and dust surrounding a tiny solid nucleus. This cloud is constantly replenished by sunlight, vaporizing the nucleus's surface. But Atlas no longer had a large, single surface. It had shattered into a collection of smaller pieces. Initially, this catastrophic breakup would have caused a surge in brightness as a massive amount of new material was suddenly exposed and vented into space, and astronomers looking back at the data realized they had seen it a brief final flare-up before the terminal decline. It was the comet's death rattle. After that initial outburst, the smaller fragments with less surface area and less total ice simply couldn't sustain the same level of activity. They were like scattered embers from a once roaring fire, each glowing for a short time before inevitably fading. We weren't watching a single light being turned down. We were watching 1,000 smaller lights being extinguished one by one. The single bright beacon of hope we had tracked for months was now revealed to be a cosmic crime scene. The initial pangs of disappointment, the sorrow for the lost spectacle, quickly gave way to a profound sense of awe and excitement. What we had lost in celestial theatre, we had gained in scientific opportunity. This was a gift of a different kind. The chance to watch a great comet blaze through the sky is a wonder, but the chance to watch one die to perform a celestial autopsy from millions of miles away is an unprecedented scientific privilege. The event transformed our entire mission. We were no longer observers waiting for a show. We were now forensic astronomers sifting through the wreckage of a cosmic catastrophe, trying to understand what terrible forces had torn this icy mountain apart. The focus shifted instantly from the whole to the parts. The questions were no longer about how bright Atlas would get, but about the fragments themselves. How big were they? How fast were they drifting apart from one another? Did they all share the same composition? Or were we seeing the stratified layers of the comet's interior now laid bare for our inspection? Each fragment was a time capsule, a piece of the original protoplanetary disk from which our solar system was born 4.5 billion years ago. Studying them was like studying the individual pages of a book that had been violently ripped from its binding. The king was dead. The brilliant monarch that had promised to rule our night sky was gone, shattered into a dozen fading princes, each on its own trajectory of decay. The spectacle we had hoped for had vanished into a ghostly funeral procession. But in its place, we were being given something far more valuable, a front-row seat to one of the most fundamental, violent, and instructive processes in the cosmos. We were about to learn what happens when these ancient voyagers, these frozen relics from the dawn of time, finally reach their breaking point. The story of Atlas, the great comet, was over, but the story of its spectacular death and the secrets it might reveal from its icy grave was just beginning. And the very first question we had to ask was the most elemental one of all. What could have possibly done this? And so the verdict came not in a whispered rumor, but in a torrent of photons captured by a vigilantly waiting world. For weeks we had watched it defy our models, a maverick voyager on a trajectory that whispered of intelligence, of purpose, of some cosmic rendezvous we couldn't yet fathom. The deceleration was real, a gentle but persistent braking against the inexorable pull of the Sunday. But the images from the Hubble Space Telescope, finally sharp enough to pierce the glowing haze of its coma, told a different story. A story of failure. There was no single coherent object there anymore. The heart of Comet Atlas had given out. What we saw instead was a tragedy written in scattered light, a funeral procession of icy ghosts drifting silently through the void. The single beacon of hope that had promised to blaze across our night sky had resolved into a string of faint ephemeral pearls. Atlas was not parking, it was dying. The dream of a great comet, a celestial spectacle for a generation, evaporated in that moment. But for the scientists who had tracked its every move, the disappointment was swiftly eclipsed by a new, more urgent mission. The mystery had shifted. The question was no longer where is it going, but what just happened. We were now witnesses at a cosmic crime scene, and the victim was a 4.5 billion-year-old relic of cosmic creation. The central body, the nucleus that was once a mountain of ice and rock, had shattered. The deceleration we had so carefully measured, the strange braking that fueled our wildest speculations, was now brutally recontextualized. It wasn't the signature of a controlled maneuver. It was the last gasp of a disintegrating object. The outgassing jets that once propelled it, now firing from tumbling, newly exposed surfaces of its fragments, were no longer a unified engine. They were the chaotic, sputtering death throes of a body coming undone, pushing against its own forward momentum and slowing its fall toward the Sunday. The elegant enigma had become a chaotic mess. The investigation began immediately, a celestial inquisition with the Sun as the prime suspect. An international consortium of astronomers turned their instruments from tracking a solid body to mapping a debris field. Every photon of light from those ghostly fragments became a clue. 3 primary culprits were brought forth from the annals of cometary science, 3 ways these ancient travelers can meet their untimely end. The first was a death by 1,000 spins rotational stress. A comet is not a static object. It tumbles and rotates through space. As Atlas drew nearer to the Sun, the solar energy striking its surface intensified dramatically. This energy didn't just warm the comet, it sublimated its ices, turning them directly into gas. These jets of gas erupting from fissures and active regions don't always fire symmetrically. If they are slightly off-center, they act like miniature rocket thrusters, applying a subtle but relentless torque to the nucleus. Imagine a figure skater pulling in their arms to spin faster. Over weeks and months, this constant, unbalanced outgassing can spin a comet up to incredible speeds. The nucleus of Atlas, like most comets, was not a solid monolithic rock. It was what scientists call a rubble pile, a loose agglomeration of ice and dust held together by a gravitational handshake barely stronger than a whisper. Its own self-gravity was astonishingly weak. As the rotational velocity increased, a powerful centrifugal force began to build from its core, pulling it outwards. A battle was being waged within the heart of the comet, the feeble gravity trying to hold it together versus the ever-increasing centrifugal fury trying to tear it apart. For Atlas, it appears the spin became too fast, the outward force too great. The delicate gravitational bonds that had held it together since the dawn of the solar system finally snapped. It simply spun itself into pieces, a catastrophic failure of celestial engineering. The second suspect was a more direct assault thermal shock. Think of an ice cube dropped into a glass of hot water. It doesn't just melt, it cracks audibly, shattering as the outer layers expand rapidly while the core remains frozen solid. The stress is too much for the ice to handle. Now amplify that phenomenon to an unimaginable scale. Comet Atlas was making its very first journey into the inner solar system. For billions of years it had existed in the unimaginable cold of the Oort Cloud, a realm where temperatures hover only a few degrees above absolute zero. It was a body in a state of perfect frozen equilibrium, but its long fall had brought it into a new, brutal environment. As it crossed the orbit of Mars and continued its plunge, one side of its nucleus was being cooked by the unfiltered radiation of the Sun, with surface temperatures soaring hundreds of degrees. The other side, turned away from the Sun, remained in the deep freeze of interplanetary space. This created an immense thermal gradient across the nucleus, a temperature difference of hundreds of degrees over just a few kilometers. The sunlit side expanded while the dark side remained contracted and brittle. This differential stress worked its way deep into the comet's interior, seeking out any pre-existing fractures or structural weaknesses. Microcracks, perhaps present since its formation, would have begun to grow, propagating deeper with every rotation, with every hot-cold cycle. The Sun's heat was not merely melting it. It was acting like a hammer and chisel, exploiting every flaw. For a first-time visitor, an object not tempered by previous passes through this thermal gauntlet, the shock may have been overwhelming. The structure simply gave way, not in a single explosive event, but in a cascade of fractures until the entire body crumbled. It was an ambush by thermodynamics, a violent welcome to the neighborhood. The third and perhaps most fundamental suspect was an inherent weakness, a pre-existing condition that doomed Atlas from the moment it was formed. We imagine comets as sturdy, solid objects, but the reality is far more fragile. They are primordial rubble piles, cosmic dust bunnies, composed of water ice, carbon dioxide, ammonia and methane, all mixed with dust, sand and tar-like organic molecules. They were never molten, they were never compressed under the immense gravity of a planet. They are simply the leftover construction material of the solar system, gently clumped together in the freezing darkness. Some are more tightly packed than others. Atlas may have simply been a weakling, its internal composition exceptionally fluffy or porous, its binding forces unusually tenuous. It might have been riddled with voids and cavities from the very beginning. Its journey from the Oort Cloud, lasting perhaps 1,000,000 years, was a gentle one, but the final frantic rush toward the Sun was a stress test it was never destined to pass. The increasing solar radiation, the growing tidal forces from the Sun's immense gravity, the thermal stresses, it was a multi-front assault that a stronger, more consolidated body might have survived. But for this particular comet, it was too much. It didn't just break, it unraveled like a poorly knit celestial sweater. The demise of Atlas, a bitter pill for stargazers, quickly transformed into an unprecedented opportunity for science. A cometary nucleus is typically shrouded from view, hidden beneath the brilliant, obscuring veil of its own coma and tail. We can only study the gases on the outside. Its deep interior, the truly ancient material that has been perfectly preserved in a cryogenic state for eons, remains a locked black box. But the fragmentation of Atlas had, in an act of cosmic violence, ripped that box wide open. The fragments, each a piece of the original core, were now fanning out, each one a miniature comet in its own right, each one sublimating pristine, never-before-seen material directly into space. We were no longer looking at the comet's skin. We were performing a ghostly autopsy, analysing the very heart and guts of a primordial body. The primary tool for this autopsy is spectroscopy, a technique that allows us to decipher the chemistry of distant objects with breathtaking precision. When sunlight reflects off the dust and gas boiling away from the fragments, it carries with it a hidden message. By passing this light through an instrument called a spectrograph, astronomers can split it into its constituent colours, a rainbow more detailed than any you have ever seen. But this celestial rainbow is not perfect. It is scarred with dark lines, tiny gaps where specific colours are missing. These are absorption lines. Each atom and molecule, be it water, carbon monoxide, or a complex organic compound, absorbs light at its own unique characteristic set of wavelengths. They are chemical fingerprints. By identifying the pattern of these missing lines, we can determine with absolute certainty what the cloud of gas and dust is made of. We can essentially read the comet's ingredient list from 500 million kilometers away. As the light from the shattered remains of Atlas streamed into the great observatories of Earth, the spectrographs went to work unzipping the comet's genetic code. The first results confirmed the expected, the overwhelming signature of water, the lifeblood of our own world, locked in ice for 4.5 billion years. But then the more exotic fingerprints began to appear. Carbon monoxide and carbon dioxide gases that must have frozen onto dust grains at the farthest, coldest reaches of the nascent solar system. The faint but unmistakable signature of cyanogen, a simple compound of carbon and nitrogen, the same molecule detected in comets for over a century. And deeper within the noise, the faint traces of more complex organic molecules, the very building blocks of life. We were staring at the chemistry of our own origins. This wasn't just a list of chemicals, it was a primordial recipe, a manifest of the cargo that comets like Atlas may have delivered to a young barren Earth, seeding it with the water for its oceans and the carbon chemistry needed to spark biology. The fragments were not just dying embers, they were time capsules cracked open for us to read. This detailed chemical analysis also brought us back full circle to the tantalizing mystery that had first drawn our attention to this enigmatic object, the question of its origin. At first, its highly inclined, nearly parabolic orbit screamed interstellar. It looked like a visitor from another star system, a true alien in our midst. That was why it was provisionally designated 3I, the third confirmed interstellar object. But as orbital calculations were refined, its trajectory began to look less like an open-ended hyperbola and more like a vast closed ellipse, the hallmark of an object from the Oort Cloud, a distant, forgotten member of our own solar system just now making its first trip inwards. The orbital data was ambiguous, poised on a knife's edge between ours and theirs. The fragmentation, however, offered a new court of appeal, a chemical trial. The chemistry of our solar system is unique. While the laws of physics and the elements are the same everywhere, the specific ratios of isotopes, heavier versions of common elements, can vary from one star system to the next. These isotopic ratios are set by the specific conditions in the cloud of gas and dust that a star and its planets form from. One of the most telling is the ratio of deuterium, a heavy form of hydrogen, to normal hydrogen. Our solar system has a very specific, well-measured D-H ratio, found in our oceans, in asteroids, and in other comets. If Atlas was from our Oort cloud, its water ice should possess a D-H ratio consistent with what we know. But if it was a true interstellar wanderer formed in the protoplanetary disk of another star, there was a very real chance its D-H ratio would be wildly different, a definitive alien signature. The data from the spectrographs was painstakingly collected and analysed. Teams around the world raced to measure the faint signals of heavy water sublimating from the dying fragments. This was the moment of truth. Was this a piece of our own distant family, a long-lost cousin returning home? Or was it an emissary from an unknown star carrying with it the chemical story of another cosmic neighborhood, another path to planetary formation? The very act of its self-destruction was providing us with the ultimate clue to its identity. We had torn it apart with our telescopes, examined its every last photon, and now its chemical soul was laid bare before us. The ghost of Atlas was now a swarm, a diffuse cloud of evidence drifting through the inner solar system. And as we worked to solve the mystery of its death and its identity, a new pressing question arose. What would become of the body? Where do the pieces of a shattered comet go? And so the vigil that had captivated the world for months reached its final, inevitable, heart-stopping chapter. The great comet, the object of so much hope and speculation, was no longer merely shedding pieces of itself in a cosmic cry for help. It was surrendering its very soul to the void. What we were witnessing through the unblinking eyes of our telescopes was not a slow and graceful dissolution. It was a cataclysm, a silent, terrifying crystalline explosion happening in slow motion across millions of kilometers of empty space. The main fragment, the piece we once called the nucleus of Atlas, convulsed one last time. Imagine a mountain of ancient ice and rock held together for 4.5 billion years by the cold of deep space, now caught in the unrelenting glare of a celestial blowtorch. The fissures that had webbed its surface for weeks were no longer simple cracks. They became vast canyons, then impossible chasms, blasting vaporized ice and primeval dust into the vacuum with a fury that defied its own structural integrity. There was no singular moment of destruction, no single blast. Instead, it was a cascade, a chain reaction of failures as the comet's ancient heart gave way. The rotational stresses, once a source of its stately wobble, became a centrifugal force of pure annihilation. One immense fragment, a skyscraper of frozen ammonia and methane, tore itself free, spinning wildly away from its parent. It was followed by another, and then another, a fleet of icy debris carving from the main body like glaciers falling into a dark sea. Each new piece, now exposed to the raw power of the sun, began its own violent outgassing, its own death spiral. They became miniature comets in their own right, each trailing a panicked temporary tail of gas and dust, a short-lived echo of the magnificent object they once belonged to. On screens in control rooms from Mauna Kea to the Atacama Desert, the image of a single fuzzy point of light was gone. In its place, a ghostly armada began to form, a loose, chaotic formation of dozens, then hundreds of shimmering shards. They were no longer flying in perfect formation. The subtle pressures of sunlight and their own erratic jets were pushing them apart, gently but inexorably. The tight, coherent object we knew as Comet Atlas had become a sprawling, disorganized cloud of its own remains. It was the beginning of a celestial funeral procession with the deceased itself providing the mourners. You could feel the shift in the global astronomical community, a palpable change from tense anticipation to a kind of somber reverence. The dream of a generational spectacle, a comet to rival Hale-Bopp, was officially over. That brief pang of disappointment, however, was immediately eclipsed by a singular electrifying realization. We were watching the death of a comet in unprecedented detail. Every telescope that could be pointed at that patch of sky was now engaged in a cosmic autopsy. We were no longer just tracking an object, we were documenting its complete and utter unraveling. The great spectrograph's instruments, designed to taste the light of distant stars, were now feasting on the chemical soup being released from the comet's core. For the first time, we could analyze the composition of a comet's interior, not just the sublimated gases from its surface. We were seeing the primordial recipe of our solar system, the raw ingredients from which planets were made spilled across the heavens for us to read. The data streamed in a torrent of information from a dying messenger. We measured the velocities of the separating fragments, calculating the forces that had torn them asunder. We watched their brightness flicker and fade as they tumbled, allowing us to map their irregular, fractured shapes. We saw the color of the dust change, revealing different mineralogies from different layers of the nucleus, a kind of cosmic archaeology in real time. This was the treasure Atlas had concealed. Its final spectacular act of self-destruction was its greatest gift to us. The apathetic universe had by pure chance staged the ultimate experiment right on our doorstep, and humanity was ready with its notebooks open. Over the next few days, the spectacle transformed. The violence subsided, replaced by an ethereal, melancholy beauty. The larger fragments, having vented their most volatile gases, began to dim. They were no longer bright, sharp points of light. Instead, they grew fuzzier, softer, their edges blurring as they continued to sublimate, shrinking with every passing hour. The cloud of debris, once a relatively tight cluster, began to stretch and elongate along the comet's former orbital path. It was as if someone had taken a brush dipped in starlight and painted a single, faint, wistful stroke across the black canvas. This was the ghost of Atlas, a phantom memory of its journey. It was no longer a comet. It was a trail, a stain, a whisper. The very last observations were perhaps the most poignant. Hubble, staring into the abyss with its peerless vision, could resolve only a handful of the largest dying embers, each no bigger than a house, each a pale imitation of its former self. Soon, even these faded from view, their icy bodies completely vaporized by the sun's warmth. They did not crash into anything. They did not explode. They simply ceased to be. One by one, the lights went out until all that remained was an imperceptible thickening of the dust that already permeates our solar system. Comet Atlas was gone. Its 4.5 billion year journey had ended not with a bang, but with a slow, silent, and final exhalation. And in the quiet that followed, the real work began. With the complete observational record from its discovery to its last vanishing photon, the puzzle was finally complete. Teams around the world began to synthesize the terabytes of data, feeding every measurement, every spectral line, every image into complex models of cometary physics. And out of that synthesis, the answer to the central mystery, the strange deceleration that had so perplexed us, emerged with stunning, beautiful clarity. The comet wasn't parking by applying some unknown brake. It was tearing itself apart from the inside out, and the deceleration we observed was the signature of that death throe. We had mistaken the symptoms of a fatal illness for a conscious act. Our models showed how the initial heating from the sun didn't just create the gentle, predictable jets of gas we expected. It opened deep, unstable vents in the comet's fragile crust. These jets weren't pushing it forward in a clean, consistent manner. They were chaotic, erupting unpredictably from its rotating surface, some firing forward, some backward, some sideways. Imagine trying to steer a ship powered by a dozen randomly firing rockets. The net effect was a messy, inefficient propulsion system that was ripping the vessel to pieces. The deceleration we measured was in fact the result of powerful jets firing in its direction of travel, acting as a retro-rocket fighting its orbital momentum. This wasn't controlled braking. It was a body at war with itself. This violent, unbalanced outgassing placed unimaginable stress on the comet's porous, loosely bound structure. The core, which we now know was likely a collection of smaller bodies, a cosmic rubble pile rather than a monolithic block of ice, simply couldn't withstand the strain. The deceleration was the sound of the engine screaming just before it blew apart. The data from the fragments confirmed this narrative perfectly. The way they spread out their individual velocities, their rotation rates, it all matched the models of a catastrophic rotational breakup caused by asymmetric outgassing. The mystery wasn't a mystery at all. It was a classic open and shut case of structural failure, one we were privileged to witness from beginning to end. And so we return to the question that began our journey. Did Comet Atlas park? In the most literal sense, no. Its constituent atoms will continue to orbit the sun for eternity, indistinguishable from the countless other particles of cosmic dust. But in a more profound, more poetic sense, yes, it did park. It parked its existence as a coherent, singular object. It ceased its grand looping journey through the solar system as an individual traveler. It pulled over on the cosmic highway, dissolved its form, and became one with the road itself. Its final resting place is not a single point in space, but a diffuse, invisible river of dust that will forever mark the path of its final, fatal plunge toward the sun. Future spacecraft may one day pass through this river. Future astronomers may one day detect the faint gravitational ripple of this trail of debris. In that way, the comet has achieved a strange kind of immortality, not as a brilliant point of light, but as a permanent, if unseen, feature of our solar system's architecture. It traded a fleeting moment of glory for an eternity of anonymity. The loss of the great spectacle was in the end a far greater gain for science. We learned that the death of a comet is not a simple event, but a complex multi-stage process of incredible violence and subtlety. We learned that the interiors of these icy bodies are more complex, more varied, and more fragile than we ever imagined. The data from ATLAS will be a cornerstone of planetary science for decades, a benchmark against which all future models of cometary evolution will be measured. It provided a ground truth, a Rosetta Stone, for deciphering the lives and deaths of these enigmatic visitors. The Ghost of Atlas delivered its final, most profound message, written not in light but in its own dissolution. It told us a story of cosmic fragility of immense age and of the violent beauty that governs the space between worlds. But what does that message mean for the countless other comets, silent and unseen, currently journeying from the dark frontier towards the warmth and light of our inner solar system? What other secrets are locked within their icy hearts, and what will it take to unlock them? So where does that leave us? Standing here in the silence, where a chorus of expectation once roared, the great celestial spectacle we had all been promised, the shimmering apparition that was set to grace our skies, never arrived. In its place, we were left with a ghost, a trail of cosmic dust and fading embers scattered across the interplanetary void. The story of Comet 31, Atlas the interstellar visitor that decelerated, is not one of a triumphant arrival, but of a spectacular and profoundly informative disintegration. It is a tale that begins with a bang of anticipation and ends, not with a whimper, but with a cascade of revelations whispered from the fragments of a shattered world. For a brief, brilliant moment, we thought we were preparing to witness a cosmic performance. Instead, we were granted something infinitely more valuable, an invitation to a cosmic autopsy. We were unwittingly given a front-row seat to the deconstruction of an alien artifact, a process that has irrevocably altered our understanding of what a comet can be. Before Atlas, our models for these icy wanderers were robust, built upon decades of observation, yet they were also profoundly biased by our local experience. We studied the comets of our own sun, the familiar residents and long-period pilgrims born from the Oort Cloud that encircles our planetary system. We believed we understood the rules of their existence, the delicate balance between solar radiation and internal cohesion that dictated their survival. Atlas defied those rules. Its fragmentation was not a singular violent event, but a slow, graceful unraveling, a piece-by-piece surrender to the gentle but relentless warmth of our star. This wasn't the explosive death of a firecracker, it was the slow, deliberate melting of a snowflake under a magnifying glass, and we were the ones holding the lens. The granular way it fell apart, peeling away in layers and shedding fragments that themselves continued to fracture, told us something fundamental about its construction. It was not a solid, singular rock of ice and dust. It was more like a celestial snowbank, a loosely consolidated agglomeration of primordial grains, barely held together by the faintest of chemical bonds. This structure, this almost ethereal fragility, provided the first major clue in solving the puzzle of its strange journey. The deceleration that so captured our imagination, the braking maneuver that fueled speculation of artificial origins, was intimately tied to this unique composition. As Atlas approached the Sun, it wasn't just the surface ice that was sublimating into gas, creating the jets that acted like miniature rocket thrusters. Its entire body was porous, a sponge-like matrix that allowed solar energy to penetrate deep within its core. This deep heating would have activated vast reservoirs of volatile ices, substances like frozen carbon monoxide and nitrogen, which turned to gas at far lower temperatures than water ice. The outgassing wasn't just a surface-level phenomenon. It was a global process, a boiling from within that produced a powerful, sustained, and remarkably diffuse thrust. Unlike the focused jets we see on our solar system's comets, which can send them tumbling and spinning, the outgassing from Atlas was more like a gentle, all-encompassing sigh. This pervasive, low-level force, acting over an immense period, was the engine behind its deceleration. It wasn't parking, it was evaporating. Its very substance was being converted into a braking force, a cosmic air brake woven from its own primordial fabric. The data gleaned from this extended death rattle has become a new Rosetta Stone for planetary science. By analyzing the light reflected from each successive fragment, astronomers could perform a kind of stratigraphic analysis peering back through the comet's history. The composition wasn't uniform. Different fragments revealed different chemical signatures, suggesting Atlas was built from smaller, distinct planetesimals that clumped together in the swirling disk of its home star system billions of years ago. We were essentially watching the disassembly of a primordial Lego set, seeing the individual bricks that constituted a building block of a planet that may have never formed. It was a treasure trove of information, a direct sample of the raw materials present in another corner of the galaxy. We saw evidence of complex organic molecules, the carbon-based compounds that are the precursors to life locked within its icy matrix. These were not just hints, they were direct measurements, confirming that the ingredients for life are not unique to our own cosmic neighborhood. They are ubiquitous, scattered like seeds on the interstellar winds, hitching rides on fragile vessels like Atlas. This single disintegrating comet did more to advance the science of astrochemistry than a dozen flyby missions might have, precisely because it failed so spectacularly. Its demise was its greatest gift. The failure of Atlas to become the comet of the century was in truth one of the greatest scientific successes of the century. It forced us to confront elegant simplicity of our assumptions and replace them with a more complex, nuanced, and ultimately more truthful reality. It revealed the sheer diversity of worlds that populate the galaxy. If Atlas was so fundamentally different from the comets, we know what other architectures exist. Are there comets as dense as solid rock, or others as diffuse as a cloud of smoke? Its journey demonstrated that an object's origin story is imprinted upon its very core, its birthplace, written in its chemistry and its structure. An interstellar origin isn't just a footnote in a catalogue, it is the defining characteristic that dictates its behaviour and its fate. Atlas was born in a colder, perhaps less turbulent environment than our own Oort Cloud. It was a relic from a different kind of creation myth, and when it entered our solar system, it was subjected to conditions it was never designed to withstand. It was an Arctic vessel sailing into tropical waters, its hull integrity compromised by a warmth it had never known. The sun was not just a source of light, it was a celestial blowtorch that methodically deconstructed this alien visitor, and in doing so allowed us to read the blueprints of its construction. This unprecedented event has completely reshaped our strategy for exploring these cosmic nomads. For decades, we have designed missions to chase orbit and even land on comets. These missions, like the heroic Rosetta and its Philae lander, were predicated on the assumption that the target would be a relatively stable, coherent body. Atlas teaches us that we cannot make that assumption, especially for interstellar visitors. The very act of approaching our sun might be a death sentence for them. This has given a powerful new impetus to projects like the European Space Agency's Comet Interceptor mission. This is a new class of planetary defense and scientific exploration, a rapid response unit designed to lie in wait, dormant in a stable orbit, ready to be deployed at a moment's notice. When the next interstellar object like Atlas or Oumuamua is detected on its way in the interceptor, we'll fire its engines and race to meet it far from the sun, in the cold deep space where it is still pristine and unaltered. We will no longer have to study these objects through the distorting lens of their interaction with our star. We will meet them on their own terms in their native environment. Comet Interceptor will be the direct legacy of Atlas. It will carry instruments designed specifically to analyze the kind of diffuse, fragmenting structures we witnessed. It will be prepared for a body that might not have a single solid nucleus, but rather a swarm of loosely bound components. It will be looking for the same chemical fingerprints of a foreign star system, the same evidence of primordial organics, but this time it will gather that data directly flying through the nascent coma, tasting and smelling the very essence of an interstellar world before it has been scoured and, transformed by the Sunday, we will be able to answer the questions that Atlas left hanging in the void. Was its fragile nature typical of interstellar comets, or was it an outlier? Do they all carry the same fundamental building blocks of life? By studying a new visitor up close, we can begin to build a true galactic census of these objects, understanding the range of possibilities that nature allows. We will move from a single extraordinary case study to a genuine comparative science of interstellar objects. The ghost of Atlas will essentially serve as the mission's guide, its memory informing every maneuver, every observation, every decision the science team makes. And so we are left looking forward, our gaze lifted from the fading dust trail of one messenger to the dark expanse from which the next will emerge. The journey of 3I, Atlas, has been a profound lesson in cosmic humility. It reminded us that the universe is under no obligation to meet our expectations. We anticipated a light show, a spectacle for the eyes, but were given a puzzle for the mind, a challenge that pushed the boundaries of our knowledge. It was a mystery that unfolded in slow motion, played out across millions of miles of empty space. The comet's strange deceleration, its refusal to follow the gravitational tramlines laid out for it, forced us to consider every possibility from the mundane to the extraordinary. It led us down a rabbit hole of complex physics, of outgassing and sublimation, of rotational dynamics and thermal inertia. And yes, for a fleeting, thrilling moment, it allowed us to dream. It allowed us to ask the most audacious question of all: is it parking? That question in and of itself is perhaps the most important takeaway from this entire saga. While the evidence now overwhelmingly points to natural, albeit highly unusual, physical processes, the fact that we could even conceive of that question represents a fundamental shift in our cosmic perspective. We have reached a point in our history where we are not just passive observers of the heavens, but active searchers scanning the void, not just for rocks and gas, but for echoes of something more. We are looking for fellow travelers. The strange trajectory of Atlas became a blank canvas onto which we projected our greatest hopes and deepest curiosities about our place in the universe. Is there anyone else out there? Are we alone in this vast, silent ocean of stars? The comet, in its silent, crumbling journey, did not provide an answer, but it did something just as important. It validated the question. It proved that the universe is stranger, more varied, and more surprising than we ever imagined. It showed us that objects can travel between stars, carrying the chemical heritage of their birthplace with them. It confirmed that the galaxy is a connected ecosystem, with seeds of possibility drifting from one stellar shore to another. The final legacy of Comet Atlas, then, is not in the light that it failed to bring to our night sky, but in the spark it ignited within us. It was a catalyst, a cosmic wake-up call that shattered our provincial view of comets and opened our eyes to the sheer, unadulterated wilderness of the interstellar medium. It taught us that sometimes the most profound discoveries are born from the ashes of failure. The story is not over, it is just beginning. Out there, right now, another messenger is on its way. It may be another fragile wanderer like Atlas, or it may be something entirely new, something so alien it will force us to rewrite our textbooks all over again. We don't know when it will arrive or what it will be, but we do know one thing for certain. Thanks to the lessons learned from a ghost of a comet that tumbled and faded before our very eyes, we will be ready, we will be watching. And we will be ready to ask the big questions, knowing that in the grand cosmic narrative, even the smallest whisper can change everything we thought we knew. The search continues.